All right, let's get into it. Today we're going to break down a really fascinating new paper from Google DeepMind that could seriously change how AI models are built. It's called Mixture-of-Recursions, or MOR for short, and it's all about giving these models a radically smarter way to think. But before we get into what MAR actually is, let's start with a provocative question. You know those huge, powerful language models we use all the time? They feel like magic, right? But what if I told you they're built on a foundation that is, well, fundamentally inefficient and wastes a staggering amount of energy and compute power? And that right there brings us to the core of the problem. For years, the transformer architecture has been the undisputed king. It's the engine behind pretty much every major AI you can think of. But its complete dominance has created what the researchers call a monoculture of waste. Sure, it's powerful, but it's a brute force, sledgehammer to crack a nut kind of approach. So what does this waste actually look like? Well, a few big things. First, there's uniform compute. This means every single piece of information, every token, gets the exact same super intensive treatment. It doesn't matter if it's a simple word like the or a really complex scientific concept. It's all treated the same. Then you've got these models just bloated with parameters, and they suffer from a huge memory bottleneck called the KV cache. Think of it as the model's short-term memory, and it just gets totally overloaded. The bottom line is, it's an architecture with only one gear, full blast, all the time. It just can't adapt. Okay, so if that's the problem, how do we even start to fix it? The first step is to grasp a key idea that MOR is built on. And that concept is the recursive transformer. It's all about finding a much smarter way to loop. So check this out. Instead of building an AI model with, say, 24 completely different, unique layers stacked on top of each other, imagine you just build 6 really good layers, and then you just run the data through them 4 times. See, you're reusing the same block of logic over and over again. For anyone who codes, this is going to sound familiar. It's just like using a for loop instead of copy-pasting the same function a dozen times. It's way more efficient and saves a ton of memory because you have way fewer unique parts to keep track of. Okay, so that's the first piece of the puzzle, looping. Now, let's take that idea and kick it up a notch. This is where we get to the main event. If a recursive transformer is about looping, then Mixture-of-Recursions is about looping intelligently. And this is where things get really clever. So this is the absolute game changer. MOR takes that looping idea and it adds a little brain, a tiny neural network they call a router. You can think of it like a traffic cop for information. This router looks at every single token and makes a decision. Does this one need more thinking time? A simple token might get a hall pass to exit after just one loop. But a more complicated one? Nope, you're going back in for another round of processing. It's adaptive computation, right down to the individual token. The paper has this fantastic Lego analogy. Imagine you're building a massive, intricate Lego castle. The old transformer way is like spending the exact same amount of time and effort on every single brick. But MOR? It's like having a smart helper who says, okay, these big, simple wall pieces, I can snap those together in a second. But this little detailed turret over here, yeah, that's going to need more of my focus. It just spends its energy where it's actually needed. It's common sense, really, but for an AI, it's totally revolutionary. Now, I know what some of you are probably thinking. Wait a minute, isn't this just mixture of experts, or MOE? And that's a great question, but nope, they are very different, and it's really important to get this distinction. MOE scales a model's width by adding more specialists to choose from. MOR scales a model's depth, but dynamically. The analogy here is perfect. MOE is like picking from a giant buffet with tons of different dishes. MOR is more like being a chef who decides that this one specific dish just needs to cook a little bit longer to be perfect. One is about having more choices, the other is about spending more time. So how does this little router actually work? Well, there are 2 main flavors. The first is called expert choice, and it's really dynamic. At every single loop, the router looks at all the tokens and reevaluates which ones need another pass. The other method is token choice, which is way simpler. Basically, each token decides right at the very beginning how many loops it thinks it's going to need, and that's that. You know, it's a classic engineering trade-off. Expert choice is more flexible and precise, but token choice is a lot simpler and more predictable to run. Okay, so the theory sounds amazing, right? It's elegant, it makes a ton of sense, but the billion-dollar question is, does it actually work? Well, let's get to the payoff, because the results are, yeah, they're pretty compelling. Okay, get this. The team trained a 118 million parameter MAR model, and put it up against a standard vanilla transformer with 315 million parameters. And the little guy won. The MAR model achieved better accuracy. I mean, let that sink in for a second. A model that is almost 3 times smaller performed better. And here's the kicker. They were both trained using the exact same amount of computational power. In the AI world, that is a huge, huge deal. And the good news doesn't stop there. When it comes to actually using the model, what we call inference, this approach can lead to a speedup of more than 2 times. And it makes perfect sense, right? All those simple tokens are getting out of the way early, so they aren't causing a traffic jam for the complex tokens that actually need the processing time. The whole pipeline just moves faster. So let's just quickly connect the dots on how it pulls this off. 1, by reusing parameters in that loop, the models are just smaller and more efficient to begin with. 2, by using adaptive compute, it stops wasting energy on simple tokens. And 3, it attacks that memory bottleneck we talked about by only holding onto information for the tokens that are still being processed. It's a 3-pronged attack on inefficiency.
Now, it goes without saying, no new technology is a silver bullet right out of the gate. So for a balanced view, we gotta acknowledge that this current version of Moore does have some limitations.
For instance, the routing strategy is kind of frozen in place after the model is trained, so it can't adopt later on. We also see that the performance gains aren't quite as jaw-dropping on really, really small models. And maybe most critically, this isn't a simple plug-and-play solution just yet. It requires some pretty specialized engineering to implement. So yeah, there are definitely some real-world hurdles to overcome. But let's end on this thought because it perfectly captures the whole spirit of this research. For years, the answer in AI has always been just get bigger. More data, more parameters, more power. Mixture-of-Recursions challenges that idea head-on. It suggests a future where AI models don't just get wider, they think deeper and more efficiently. And that shift from just brute force to intelligent efficiency, well, that could be what defines the entire next generation of AI.